We're now going to examine the large signal behavior of the source coupled pair. Alright, so we'll draw our source coupled pair. With an NMOS input. And what we want to do is find delta ID, which is equal to ID1 minus ID2, where ID1 is the current through transistor M1 and ID2 is the current through transistor M2. And we're assuming that M1 and M2 are identical and RD1 is equal to RD2. And we're going to do this as a function of the input differential voltage. In other words, basically what we're doing is finding the large signal transconductance. How much does the output current change due to an input differential voltage? So we know that we can define our input differential voltage, ID, or we can define our drain current through transistor 1 when it's in saturation as 1/2 mu n C ox times W over L1 times VGS1 minus VT squared, VTH squared. And we're going to make a substitution that K prime is equal to mu n C ox times W over L. If we solve for VGS1, we find that VGS1 is equal to the threshold voltage plus square root of 2 times ID over K prime. In other words, VGS is equal to VTH plus a VOV. Now we could do a similar thing in solving for VGS2. We would find VGS2 is equal to VTH plus square root of 2 times ID2 divided by K prime, assuming that the transistor's W over L is equal. We can define our input differential voltage then. VID is equal to VGS1 minus VGS2, just the difference of the voltages on the gates of the two transistors. And if we make a substitution, we'd find that this is equal to square root of 2 times ID1 divided by K prime minus square root of 2 times ID2 divided by K prime. Now we're going to define our delta ID as equaling ID1 minus ID2, and we could define ID as the average of the two currents, where ID would be the current through the current source here, and it would be equal to ID1 plus ID2 divided by 2. So we could substitute the following into this expression. ID1 is equal to ID plus delta ID over 2, and ID2 is equal to ID minus delta ID over 2. So we're going to substitute these two currents into the expression we just derived. And if we make that substitution, we could write that VID is equal to square root of 2 times ID plus delta ID over 2 divided by K prime minus square root of 2 times ID minus delta ID over 2 divided by K prime. Now what we want to do is solve for the delta ID term in terms of VID, and if we do that we find an expression delta ID is equal to K over 2 times VID times two ID over K prime over 2 minus VID squared. Square root of that whole quantity. Now if we realize that our input differential voltage should be a small signal, because this then VID squared should be much smaller, so we can neglect this term, and if we do that we would find that delta ID is equal to 1/2 mu n C ox times W over L times the input differential voltage times the square root of 2 times the drain current divided by 1/2 mu n C ox times W over L, which kind of looks like an overdrive voltage. So if we were to plot this, delta ID versus the input differential voltage, we see that it has a square root dependency. So we should get something that looks like this, where this curve represents ID2, and this curve represents ID1. Now these would have a peak value of ID, which was the value through our current source. They would cross the y-axis at they would cross the y-axis at ID divided by 2. In other words, half the current would be, when the differential voltage is equal to 0, half the current would go through one transistor and half the current would go through the other. And the slope of this curve is equal to big GM for our transistor. Now one thing that we might note then is that GM is equal to delta ID by delta VID, and its maximum right at the 0 crossing, so the maximum occurs in here. And the other thing is that this slope is dependent upon the overdrive voltage for the transistors. So if we define a different overdrive voltage, in other words by changing the size of the device or the bias current through the device, we could get a different slope of this curve. And we would note that this VOV prime here that would yield this steeper curve or larger GM. Causes the usable range for the device to be smaller. So we can only use this device where we have this fairly linear relationship. So what we see here is that VOV double prime for the device being less than VOV prime we have a larger usable range for our VOV prime. So we could say increasing VOV increases the usable range for our device. All right. So in the next set of slides, we'll look at what we need to make a couple of assumptions about the valid range for these devices. So what range of voltages at the input, what range of input differential voltages is this valid over? And if we want to increase the linear input range of our device, how do we do so?